Hello, everyone. Welcome back to our seminar. Today, Carolyn Reinhart is going to tell us about the non-backtracking matrix.
Thank you, and thank you for the invitation. So this is joint work with some of my collaborators, Kristin Heysse, Lorenzen, and Xinyu Wu. And it started at a AIM workshop, American Institute of Mathematics, and it was also continued this past summer at the Simon's-Laffer Math Institute, formerly MSRI. Right, let's see. So here are my collaborators. You can see some of us out there and riding the cable car in San Francisco. All right, so first, just a brief introduction. What is spectral graph theory, which this falls under? So we're going to associate a matrix with a graph. We're going to look at eigenvalues, and we're going to learn information about that graph, hopefully. Starting with the adjacency matrix, which is not the matrix we're going to study, but we're just going to use it quickly as an example. So the adjacency matrix we're probably all familiar with. You're assigning a 1 when there's a edge between two vertices and a 0 otherwise when there's not an edge. And so what we want to look at, we're going to look at matrices and eventually eigenvectors. So what I want to first mention is what happens when we multiply the adjacency matrix by a vector x. So let's suppose that we had the vector x, 1, 1, 1, 1, and we can think of it as assigning 1 to every vertex of our graph. And we can think of each edge in our graph as being bidirectional. So what happens when we do a times this vector x? Well, what we're really doing is we are adding up the neighbors of those vertices. So if we look at the center vertex, it has 3 neighbors. And so when we do a times x, we get a 3 in that spot. Okay. So this is just any vector, but we could also do it with an eigenvector. And so this is an example of a vector that is an eigenvector, 0, 0, 1, negative 1. And we can see that when we multiply a times x, which in this case, again, is summing the neighboring values, we see that this is an eigenvector because you get negative x out. So it's an eigenvector with eigenvalue negative 1. Okay. All right, so let's go to some linear algebra facts, and then we'll get back to graphs. So just so we're all on the same page, we can say that a matrix, an n by n matrix, has n eigenvalues, and we can order them if they're all real, which actually isn't going to be true in a minute. But and then we can look at the algebraic multiplicity, and we can also look at the geometric multiplicity. And ideally, these things would be equal, and they are in real symmetric matrices, like our friend, the adjacency matrix. But they are not going to be equal for the non-backtracking matrix necessarily. There we go. And so if a matrix is n by n real symmetric, then it has n real eigenvalues, it has n linearly independent eigenvectors, and it is diagonalizable. And that is our favorite situation, but it's not going to be where we're going to stay. So we also need a tool called the Jordan canonical form. So when a matrix doesn't have n independent eigenvectors, it isn't diagonalizable. And the Jordan canonical form is the next best thing. So just as a reminder, here's what Jordan canonical form looks like. It's a matrix that is similar to the matrix that we started with, and it's block diagonal, where the blocks have eigenvalues on the diagonal, and then on the superdiagonal is all 1s. Okay, so this is sort of almost diagonal. And if we want to think about what does the Jordan canonical form look like, well, for a matrix, we can look at the generalized eigenvectors of an eigenvalue by looking at the null space of m minus lambda I to the k power. So what does this look like? This forms the generalized eigenvectors along with the eigenvector and the eigenvalue form what we call a Jordan chain. And so the eigenvalue and the eigenvector have this relationship that we're all familiar with. MV equals lambda V, M minus lambda I times V is 0. And the generalized eigenvectors are sort of moving up the chain. And so the first generalized eigenvector, when you do M minus lambda I times that vector, you get back the original eigenvector. And that's the same thing as saying that M times U1 is lambda U1 plus the eigenvector. And so we can keep going for as many generalized eigenvectors as we happen to have. And this is what we call the Jordan chain. And the length of the Jordan chain, which is the number of generalized eigenvectors, this is going to be what tells us the size of our Jordan blocks. So if we have a Jordan chain, if we have a generalized eigenvector at all, then we know we have a Jordan block that is more than just a single entry. It's a non-trivial Jordan block. All right, now let's go back to graphs for a second. All right, so a random walk is a process from moving along a graph. Either we can say from vertex to vertex or edge to edge, where at any given time the next vertex is chosen according to some probability distribution. And so we could move from this to this, and now we're at a vertex, and we have to decide where to go next. And so in a random walk, we could go to any direction next, and it's going to depend on the probability distribution. But in a non-backtracking walk, we can't move along the edge we just went across. So we've just moved forward along this edge on the left, and so now we can't return backwards, but we can go forward along any of the other edges, leaving this vertex. Okay. And we can have non-backtracking random walks. In this talk, we're not going to be talking about the random aspect so much, but that's definitely related here. All right, so now let's get to the non-backtracking matrix. This is what I said I was going to talk about. All right, so we want to store this information about non-backtracking walks in a matrix. So what we're going to do is we're going to let this matrix be edge by edge. And in fact, it's 2 times the number of edges by 2 times the number of edges. And that's because we are letting each edge be 2 bidirectional edges, or be 2 directed edges, excuse me, where we are going to let an entry in the matrix be 1 if and only if those edges can be traversed in succession, and a 0 otherwise. So looking at our favorite example again, we make all the edges into these 2 directed edges. And we can look at the first row, which corresponds to the edge 1, 2. So after I move from vertex 1 to vertex 2, I can move next along the edge 2, 3, or along the edge 2, 4, but that's it. All the other edges I cannot move along, either because they're not adjacent to, they're not leaving the vertex 2, or they are the edge 2, 1, which I can't backtrack along. All right, and here's the rest of the matrix that we can just fill out. I do want to note one thing here, which is that this is a nice small graph on 4 vertices. And even here, we see we have this huge matrix already. So it's a pretty unwieldy matrix to work with, which is a little bit annoying, certainly, in terms of looking at examples and trying to get some results on it. All right, so just a brief history about this matrix. So it was first defined in 1989 by Hashimoto in a paper about zeta functions of finite graphs. And it has since been used in a lot of applications. In particular, it's been used to study non-recurrent endemic spread, using that non-backtracking idea. And also, I want to point out that the eigenvectors are important. So people have used the eigenvectors to look at the importance of nodes in networks. And so we really care about when we have eigenvectors and when we don't. And more recently, the non-backtracking matrix has caught the attention of spectral graph theorists. So the spectrum of the matrix was studied by Glover and Kempton in 2021 and by Torres in a 2020 plus paper. And both of these papers sort of inspired our project that we're working on, where we study the Jordan canonical form of the non-backtracking matrix, which is a logical step since it is a non-symmetric matrix and we don't know that it is not diagonalizable. All right, so here is some known results about the non-backtracking matrix spectrum from the Torres paper. So just as a reminder here, geometric multiplicity is GM and algebraic multiplicity is AM. And I want to note a couple things. So first, let's look at this first line, which is about when 0 is an eigenvalue of the matrix. So note that right away, we see a difference between the geometric multiplicity and the algebraic multiplicity. So the geometric multiplicity is the number of leaves, and the algebraic multiplicity is 2 times the number of non-cycle vertices. So right away here, we're going to get a lot of cases where we have non-trivial Jordan blocks for the eigenvalue 0, okay? So we're actually going to end up restricting ourselves to the case where we have minimum degree at least 2. But first, let's look at this a little bit more. So we can say that the 2 core of a graph is the maximal induced subgraph where the minimum degree is at least 2. And the 1 shell is everything else, which is the tree-like parts. So if you look at this example graph, we could peel off a leaf, which is 4, and then we could peel off another leaf, which is 3. And now we're left with this cycle. So if we take off all the parts that are like trees in some sense, then we are left with this 2 core. And we can see in this example, I've highlighted this x to the 4th because that x to the 4th is coming from those 2 pieces of the 1 shell, that vertex 4 and vertex 3. So each 1 shell vertex contributes x squared to the characteristic polynomial. So we're going to basically not look at this case where there is a 1 shell. We're going to look at everything where the graph is a 2 core. Okay. So the next result I want to highlight is this case of when lambda is equal to 1 or -1. And so we have this well-known, or we have this exact description of the geometric and algebraic multiplicity here. And you can see it's the same. So that there's no gap here in the algebraic and geometric multiplicity. This +1 in parentheses is for bipartite graphs. So you get that +1 for bipartite graphs, and you don't get it for non-bipartite graphs. And so here's the result I was just talking about. So in particular, this is true for graphs that have at least 2 cycles. So if G is a graph with at least 2 cycles, then the eigenvalue 1 has algebraic and geometric multiplicity m minus n plus 1. And that's for eigenvalue 1, and for eigenvalue -1, this is true with a +1 for bipartite and not for non-bipartite graphs. And I want to point out sort of, what does this mean, this at least 2 cycles? How does it interact with our notion of looking at just the 2 core? So the 2 core of every graph is either a cycle or contains at least 2 cycles. So if we're restricting ourselves to graphs who the whole graph is a 2 core, meaning there's minimum degree at least 2, then either that graph is a cycle or it contains at least 2 cycles. So we can take this result for granted if we're not looking at the cycle graph, basically, for our results. And that'll come up again later. All right, the last thing I want to highlight here was this conjecture, which is basically that the geometric multiplicity and the algebraic multiplicity of an eigenvalue are both 1 for eigenvalues that are between 1 and the spectral radius. And another way of saying that, or a larger conjecture that includes that idea that Torres made, was that the non-backtracking matrix of G is diagonalizable if and only if G has an empty 1 shell. And so we set out to look at that conjecture and prove it wrong. So the questions we started asking was, do there exist graph with minimum degree at least 2 that do not have a full set of eigenvectors? And if so, can we say anything about what the graph structure is going to look like? So what did we do? Well, we started by generating a lot of examples. And then we looked for graph structure patterns and related that graph structure to eigenvectors and generalized eigenvectors. All right, so this little cluster of symbols is graph 6 strings. So they come from running the Naughty program on Sage. These are graphs on 8 vertices, and the arrows indicate subgraph relationships. So you can see there's this highly related structure in between these graphs with, these are graphs that have an eigenvalue which is missing at least one eigenvector. And notably, there's only 2 eigenvalues that happen. You have the eigenvalue plus or minus square root of 2i for roughly half of the graphs, and you have an eigenvalue lambda equals -1 plus or minus square root of 7i over 2 for the roughly the other half. And note that both of those have eigenvalue magnitude square root of 2. All right, and so here's what they actually look like. I know that wasn't that informative, that picture. Here's what they actually, some of them actually look like, not all of them. And you can see there's a lot of repetition happening here in the structure. There's sort of 2 groups of graphs that we see. So we have this first graph on the top left, and then all these other graphs are some way that we've added edges to them. And then on the bottom right, we have this family of graphs where, again, you have sort of a starting graph and then all these graphs where you've added edges somehow. All right, so we're going to focus in on the first type of graph. And through just examination and staring at them long enough, we were able to determine that all the graphs in this family of graphs that we got were some manipulation of these 4 special vertices. So the other 4 vertices, you can't touch them. But these special vertices, we can add edges in between them. So in particular, here's our result. So if you have this graph on 8 vertices, then we can construct an infinite family of graphs with a degenerate eigenvalue, with an eigenvalue that has a missing eigenvector, by adding any edges in amongst those special vertices. And also you can add in any other graph by identifying a subset of the graph onto these 4 vertices. So you can plug anything in, you just can't touch those other 4 vertices. All right, so let's talk briefly about how we prove that. So the idea is that we can construct very nice vectors, both eigenvectors and generalized eigenvectors for this graph. And then what we do is when we add a new edge, because remember the non-backtracking matrix is 2 edge by 2 edge. So we really care about adding edges, not about adding vertices. So when we add a new edge, what happens is we just add a 0 in that entry of the vector. Okay, so here's what our vector pattern looks like for our eigenvector, where all of the a's are 1 and all of the b's are square root of 2i over 2. And just like before when we talked about the adjacency matrix, if we want to think about what happens when we do b times a vector, we can think about what's happening on the graph. So what happens when we do BV is we are summing the vector values for the edges that are outgoing, that the next edges that we could walk over, remembering that we can't backtrack. Okay, so what does that look like? Well, let's focus in on this edge in red, which has an A on it on the top left. And what are the next edges we can move to? Well, after we move along that edge that has an A, we could move along the two edges that have a green A and a green negative A, or we could move along the edge which has a negative 2B in green. So we have to sum up that A minus A and negative 2B. And that should be equal to lambda times our value of our edge, which is A. Just to clarify, I realize I didn't quite say what's going on here with the two graphs. The reason I have two graphs next to each other is just because I need to display a value for each edge going in each direction. And so in order to have some way of doing that, this is how I've decided to display it without it being super confusing. So hopefully everyone can understand what's going on at those two graphs. All right, so we can see here that I've found an eigenvector. If you believe me that negative 2b is equal to lambda a, hopefully you can check the math and it works out. So what happens then if we add an edge? So I've added an edge now between the top two of my red vertices. So on the left, I have the edge going down, and on the right, I have the edge going up. And I'm going to add a 0 to them because I said that's what I'm going to do when I change my graph. I'm just going to throw a 0 in my new vector value. So now if I do the same thing, I add up all the edges leaving. After I've traversed A, I can traverse A, 0, negative A, or negative 2B on the right. And again, that's going to be equal to lambda A. And this same thing holds no matter how many edges we add within those red vertices, or if we add even a whole new piece of the graph, as long as it's only hooked into the red vertices. All right, then what we can do is we can look at the generalized eigenvector. And a similar pattern holds. Now we have these C's and D's where C is root 2i and D is 1/2. But now we need a slightly different thing to happen. So we're still going to add up the adjacent edges. So after we move across this red 0 edge, we go along the green edges, which is negative C, C, and 2D. But now we need that to be equal to lambda times 0 plus A, where A is the value from the edge in the eigenvector. Okay. So again, you'll have to trust me that this math works out. But it's the same thing, which is that basically 2D is equal to A. All right. So that was our first pattern. And it worked out very, very nicely. It's mostly just some algebra once we found a nice pattern for our vectors. Okay, so we were hoping that the same thing would be true for the second pattern, and it wasn't. It didn't work. We did identify that there were these 4 special vertices again, where again, it seems that we can plug anything into these vertices, but the eigenvectors and the generalized eigenvectors just were not nice. We were able to get the eigenvectors to work out, but not the generalized. So if you get stuck and you don't like the matrix that you're working with, try a different one. So now we're going to talk about a different matrix that has the same eigenvalues. as the non-backtracking matrix. And that to do that, we're going to look at this matrix K. So we define K to be a block matrix with the adjacency matrix, and then the degree matrix is D, minus the identity, and then minus the identity, and then 0. And this matrix has characteristic polynomial x squared I minus xa plus d minus I. All right, and there is a well-known theorem called Ihara's theorem, which shows that the characteristic polynomial of which shows that the determinant of I minus ub, so that's not quite the characteristic polynomial of the non-backtracking matrix, is equal to this polynomial here. And if you plug in u equals 1 over x, you see that the eigenvalues of the non-backtracking matrix are plus and minus 1, and also the solutions to this polynomial, which is the solutions to this determinant of this polynomial, which is the same thing we have up here. So that tells us that K has the eigenvalues of the non-backtracking matrix, except for some plus and minus 1s. Exactly m minus n of 1 and m minus n of minus 1. All right, so there is these matrices S and T and tau that we can define, and they're going to help us build this sort of relationship that we need between the K matrix and B. So these can be defined. S is a matrix of terminal instance, so it's an edge by vertex matrix where if an edge ends at a vertex, we get a 1. T is an initial instance, so if an edge begins at a vertex, we get a 1. And then tau is the backtracking operator, so it shows where is backtracking happening. All right, and it's not so important that we understand these, but basically using those matrices, we can define this relationship between B and this bigger matrix M, where M has K in the upper left corner, and then it has the identity matrix and the negative identity matrix, which is just in order to account for those plus and minus 1s that we were missing. So this says that Bx is equal to x times this matrix M. And we have not just that we have this, this similarity between them, but we specifically understand this matrix X. X is defined to be the matrix S T transpose R. Okay, so and this matrix is, as I said, it's exactly going to have the matrix, the eigenvalues of K, and then with that plus and minus 1 that we were missing. All right, so we're going to be using this result. This result just shows that the eigenvalues are the same. But we actually wanted to show that the Jordan canonical form was the same for this M matrix and our non-backtracking matrix. Okay, so what we did is we said, let's look at graphs that have minimum degree at least 2. Then the non-backtracking matrix and this matrix M, which again has K as the big part with those additional identity matrices. And B and M have the same Jordan form unless G is a cycle, in which case the Jordan form only differs for the eigenvalue 1 when n is odd and plus or minus 1 when n is even. Okay, so this is an outline of the proof we're going to do. So first, if M has a non-trivial Jordan chain, then it must be that it's lifted from K, where by lifted, I just mean the non-zero parts are from K, and then we add zeros. we will also show that if xv for some vector is non-zero, then lambda, xv, and xui is a Jordan chain for the non-backtracking matrix. If xv is 0, then v can only be a very specific vector. And lambda is plus or minus 1. And then lastly, we leverage the known information about the lambda equals plus or minus 1 case. Okay, so let's go through this. So first, suppose that K has an eigenvector V prime with eigenvalue lambda. So if we look at B times Bx times the vector V prime with zeros padded down below, then we can just plug in the Bx equals xm, and we can see that it follows that x times this vector with V prime 0, 0 is an eigenvector for eigenvalue lambda for the non-backtracking matrix. All right, and if we let this lambda v ui be a non-trivial Jordan chain for M, then we have that this v prime 0, 0 and ui being u prime 0, 0. Those are going to be a Jordan chain. Well, we are building those from a Jordan chain of the matrix K. So first, let's assume that xv is non-zero. Well, then we already showed that xv is an eigenvector of B. And if we look at the Jordan chain, then we can see that the fact that bxu is equal to lambda xu plus xv, and we know xv is non-zero, this implies that xui is non-zero. And so xu1, sorry, is non-zero. And so this continues, and we start a Jordan chain. All right, so now let's look at maybe the more interesting case, which is what happens if xv is equal to 0. So in other words, we happen to have a vector that's an eigenvector for our K or our M matrix, rather, but it is in the null space of this special matrix X that we used for similarity. Well, it turns out that it can only be a very specific vector. So why should that be? Well, I told you how X was built. And in particular, the part of X that's going to be interacting with the non-zero part of our vector, which is V prime, is ST transpose. Okay, so ST transpose V prime is equal to 0. And what that looks like is V prime is going to have two values for each vertex, a terminal and an initial. And we need those two to be summing to 0. So this is partitioning our vertices into two sets. Okay, and so what we see is that the vertex A, this vertex with a green A on the left, has a initial, that edge has an initial vertex on the left and a terminal vertex in the middle. So those two green values need to add to 0. So we have A and negative A. They need to add to 0. Then continuing, we need negative A and A to add to 0 on the right green edge. And so this sort of partitions our set. We could do the same thing with the other edges and get these B's. So we have basically that the left and right vertices are in a set and the middle vertex are in a set. So if there is an edge in that set, then we can't really partition them. And this then implies that A is equal to negative B. The partition they all have to actually be in the same set. They all have to have the same value. So if we let A be equal to negative B and do some algebra, we end up showing that we have this exact eigenvector and we have lambdas 1. On the other hand, if there are no edges in amongst our sets, then the graph is bipartite because we managed to partition our graph into two sets. Okay. And so then we can rewrite our matrix in a bipartite manner and do some more algebra. And we end up getting some very specific relationships between A and B, which shows us that lambda is plus or minus 1, and we specifically have these patterns for our eigenvectors. All right, so what have I said all of this for? Well, first of all, we said that if lambda is not equal to plus or minus 1, then our eigenvectors and our generalized eigenvectors from K, we can exactly translate them to B. We know how to do that. Also, when lambda is equal to plus or minus 1, we have a special case, but we know what's happening in that case. Okay, so recall that if G is a graph with at least 2 cycles, then we know exactly the multiplicities, the geometric and algebraic multiplicities for the bipartite and not bipartite case. And both have a full set of eigenvectors. Okay. And so in particular, the multiplicities are m minus n plus 1. But recall that we have m minus n in our characteristic polynomial that we had written down earlier. So that means plus or minus 1 could appear as a root for k. It could be an eigenvalue of k, but at most once. So that means that we're not going to get a degeneracy there because we only have one algebraic multiplicity or 0 for k. Okay, so if G has at least 2 cycles, then we don't have to worry about a failure to have a full set of eigenvectors for the plus or minus 1 case. And let's just remember what happens when we have less than 2 cycles, but a minimum degree of at least 2. That's the cycle. Okay, so that's why this is the special case. So this case results in a graph which has a non-trivial Jordan chain for K, but not for the non-backtracking matrix. So this cycle graph is the only problem case where our relationship does not hold. But in all the other cases, we can exactly translate between the two. All right. So just wrapping up here, what have we done? So we found one infinite family, excuse me, which has generalized eigenvectors that lift very nicely. And we were just able to use the non-backtracking matrix for that. And then we turn to this matrix K, which has made it easier to look at generalized eigenvectors because in particular, the matrix K is vertex by vertex, or it's larger than that, but it's 2 vertex by 2 vertex, but it's indexed by vertices instead of edges. And that makes it sort of, in some ways, easier to understand. And then we looked at all the degenerate graphs on 8 vertices with minimum degree at least 2, and we can see that they're all explained by 2 families exactly. So what's our future work? So all of our second family have the same degenerate eigenvector, but the generalized eigenvectors are a little less predictable. But we have hope that we can understand them more fully using K. The eigenvectors for K are a lot nicer than the eigenvectors for the non-backtracking matrix. And looking at graphs on 9 vertices, interestingly, 324 are from family 1, 156 are from family 2, and there are 3 remaining graphs that don't fit into either family, but they're weird. And so maybe they're algebraic accidents or maybe they're starts of new families, but they don't fit our patterns that we expected. And then we're also working on relating graph structure more to the degeneracy, including twin vertices seem to be a promising direction. Right, and that's it. Thank you.
Okay, thank you so much.